I want you to imagine a circle that is rolling along a table. And I want you to imagine as that circle rolls that you've picked a point on that circle and you follow that point on the circle as it rolls along the table. Actually, you're not going to have to imagine that. I have a video of that for you that I'd like you to watch. So we're going to focus our attention on the point at the top of the circle and watch the curve that that point traces as the circle rolls along the table. Okay, so now it's at its very lowest. Going to come back up again as the circle continues on. As it reaches its maximum height, that's going to occur when the y value is at exactly twice the radius of the circle, or one full diameter of the circle. And then the point comes back down to the table again, and then we start all over. Okay, so we're going to spend some time discussing this curve. It's an interesting curve. It's called the cycloid. It was first named in 1599 by Galileo. And it was the subject of a couple of questions that were asked some time ago. Let me refer to the whiteboard over here. So one question that was asked in 1696 by, well, a man that you're already somewhat familiar with, Johann Bernoulli, famed for Bernoulli's rule, or what many refer to as L'Hopital's rule. Bernoulli, of course, was the inventor of that rule. But anyway, he was also the proposer of this question. He asked, given 2 points in space, A and B, with B lower than A, along what path will an object travel from A to B in least time? It's an interesting question. It might sound like it's a question that is that's obvious. So, right, so if we have a couple of points, some point A and some lower point over here that we'll call B, along what path will an object travel, or think of it as a ball rolling, in least time? And I mean, it seems like a natural answer would be, well, a straight line. I mean, a straight line is going to be the curve of least distance. But as you think about it a little bit, an object falls a lot faster whenever it's moving straight down. So maybe the curve might be one that has the object in free fall for a while, and then goes from that lower point to point B. Or maybe it looks something more like this. I don't know, maybe it looks something like this. The question is, which path is it that takes an object from A to B in the least amount of time? Well, Bernoulli not only proposed this question in 1696, he also solved this question in 1696. Other mathematicians looked at it, Newton amongst them. I believe Newton solved it also. And it turns out that the curve that does the job is, well, obviously not the cycloid. That wouldn't make any sense, but an inverted cycloid. So if we turn that cycloid upside down, turns out that if we've got a point A there and a point B there, then the cycloid, the inverted cycloid, is the curve along which the object is going to travel in the least amount of time. There was another question that was asked a little bit earlier than this one, and that was along what curve will the period of a rolling ball be independent of starting position? Now, this is ignoring friction, right? So what we're asking here is, so if we've got an object that's going to go from let's say this point right here to this point right here, right? We're ignoring friction, so the amount that it falls is going to be the amount that it rises as well. There's going to be some time period that elapses as we go from one point to the other. We want to know along what curve will we go from one point to the next, and then it's going to roll back again. That's independent, for which the time required is independent of the starting position. So if we started there and wound up here, right, we want the same amount of time to elapse. And the answer to that, again, is the inverted cycloid. This particular question was answered by Christian Huygens in 1673, right? So slightly before the Bernoulli problem was proposed and answered. And interestingly, for the literary amongst you, Herman Melville refers to this curve in Moby Dick. Go find your copy of it and check out chapter 96. See if you can find it. We're going to spend some time studying this historic curve as a primary example of a curve that can be written in terms of what are called parametric equations. We'll talk more about what that means as we get a little bit further along. But for now, I'd like to take you to our whiteboard, and we'll begin our study of the cycloid. What I have here is a sketch of the cycloid. Have a copy of the generating circle here with a point sitting on the table, so this is the circle's starting position. And as the circle rolls along, right, as it spins along, that point is going to move along what I've drawn in as this red curve at this point here. This is the point at which we're going to be doing most of our investigation. Whenever it gets to this point, the circle has revolved by theta, some theta number of, we're going to use radian measure to describe this angle. So it's going to have gone through an angle of measure theta radians. And what I'm interested in is a way of describing this curve algebraically, right? So in other words, what I'm looking for is a way to express the pair of coordinates x and y at a particular point whenever the value of theta is, well, theta. So here's the idea. We're used to looking at curves being described in terms of functions, y equals f of x. That's going to be particularly difficult for this particular curve. What's going to be easier for us, a whole lot more straightforward, is to describe what the value of x is at some given theta value, and then what the value of y is at that same given theta value. What we'll have then is an equation for x in terms of theta and an equation for y in terms of theta. That pair of equations is referred to as a pair of parametric equations in terms of the value theta. Theta will be referred to as the parameter at that point. So here's the idea. Let's start with y. Let's start with the value of y. And I think it's pretty clear that if this circle has radius r, that the y value, the y coordinate, is going to be this value of r plus, well, let's see. Let me draw a triangle here. Right there. So it's going to be the value of r plus this length right here, right? So the value of r plus the opposite side of this angle. And I'm going to label this, we'll label it h for, looks like a height, right? So, so let's just notice that y, write it down here, y is going to equal the radius plus whatever that value of h is. Well, and I think it's also clear that, let's see, if I took h and divided it by, well, this is also r, isn't it? If I took h and divided it by r, what I get is the sine of this angle. Of course, what is that angle? That's the angle, well, it's all of theta with a right angle taken out of it, so theta minus pi over 2. So h over r is equal to the sine of theta minus pi over 2. And that makes h equal to r times the sine of theta minus pi over 2. So we have y is equal to r plus r times the sine of theta minus pi over 2. Which I guess if you wanted to, we could re-express that as factoring r out, r times 1 plus the sine of theta minus pi over 2. Great, we're halfway there. We have a description for y in terms of theta. Let's go for x. Well, let's see. I think it's maybe not as clear, but it's not too hard to see that if we measured the length from the starting point over to this point right there, well, we've certainly gone beyond x, right? X lives right here. But if we took that length and subtracted off this length, I'm going to call this length k right here. If we subtracted off k, we'd have x exactly. And k happens to be the length of the adjacent side of this angle, theta minus pi over 2. Right, so let's write that down. So x, so far we have it as this full length right here. Let's call that L. It's L minus k. And k, we should be able to find that similarly to the way we found h over here. Right, if I took k and divided r into it, I've got the cosine of theta minus pi over 2. Right, so what do we have? So k divided by the radius of the generating circle is the cosine of theta minus pi over 2. So that tells me that k must be r times the cosine. So I'll just replace k with r times the cosine of theta minus pi over 2. And now all we need to figure out is what L is. Well, we're going to have to do a little bit of review for that. So let's ask ourselves, if we've got a circle, radius r, and I've got a sector of it with theta being the angle of that sector, and we often use s to denote the arc length of a sector of a circle. What's the relationship between theta and S and R? Well, here's what I want you to notice. If I doubled the angle, of my sector, what's going to happen to the arc length, right? What's going to happen to, how's the arc length going to compare to the arc length of the original? Well, if I double the angle, I think it's clear that the arc length is going to double as well. One way of noting that is that if I took, let's see, S divided by S prime. So let's see, so I've doubled the arc length. So S prime has twice the arc length of S, and so this is going to be a half. But the angle doubled also, and so theta divided by theta prime, I'm going to call this whole angle theta prime here, theta divided by theta prime is also going to be a half. What would have happened if I had tripled it instead? Well, if I had tripled it, then instead of a half each time, I'm going to have a third each time. Point being that S over S prime is always going to be the same as theta over theta prime. Now, if we only knew of some circle for which the arc length and the angle were known, then I would be able to figure out what a relationship was between S and theta. But I do know of such a circle or such an arc length. In fact, I know a lot about the arc length of the entire circle and the angle of the entire circle, right? If I started here and went all the way around and measured that arc length is the circumference of the circle, 2 times pi times the radius. And the angle is 2 pi. So S divided by, well, 2 pi r must be the same as theta divided by 2 pi. So a little algebra tells me that S is going to be equal to, let's see, what is this? 2 times pi times the radius times theta, all divided by 2 times pi. Well, that's just the radius times theta. And that's the relationship between S and theta. So if we apply that back to our problem here, let's see, so well, how can we do that? We're looking for L. How does this sector of a circle thing help us? Well, as the circle revolved along the table, as it rode along the table, every one of these points, right? So we started with this point touching there. Every one of these points up until now, this one, was at some time along the table, right? Whenever we were this far along, it was this point. Whenever we were this far along, it was this point, right? And so what we can see is that this length L is actually the length of this sector. But I now know how to find the length of that sector. It's R times theta. So that's the piece we were missing. L, this length, is the same as the length of this sector, and that's R times theta. And so I can write X as R times the quantity theta minus cosine of theta minus pi over 2. So I have X is equal to r times theta minus cosine theta minus pi over 2. And y is equal to r times 1 plus sine of theta minus pi over 2. And this is a pair of what we call parametric equations, right? Parametric refers to a common parameter. Theta is our common parameter. So parametric equations, which describe this curve that Galileo called the cycloid in 1599. Now, there's actually a slightly simpler way of writing these down, and that's all we want to do is simply note that theta minus pi over 2 shifts the cosine function a bit. Let's see. So if I drew the graph of cosine, call that 0, call this 1, -1. So cosine looks a lot like this, right? And if I shifted pi over 2 units, if I shifted pi over 2 units, that's going to take the whole curve and shift it in this direction by pi over 2 units. So it's going to take this point, which is at negative pi over 2, and put it there. And my curve is going to become the graph of sine of theta. And so I could write x instead of the way I've written it. I could write it as r times theta minus sine of theta. And similarly, I could write y as r times the quantity 1. And let's see what's going to happen to sine. So if I took the graph of sine and shifted it this direction by pi over 2 units, I'm going to wind up with, should be way down here, shouldn't it? I'm going to wind up with the opposite of cosine. So instead of sine of theta minus pi over 2, I can write the opposite of cosine of theta. And this is the pair of parametric equations that is traditionally written down for the cycloid. There are plenty of questions that we can ask about the cycloid that are of a calculus nature. We could ask things like, what is the area, for example, under the graph of the cycloid for, say, one period of the cycloid? We could ask, what's the length of the arc of one period of the cycloid? We could revolve the cycloid, the graph of the cycloid, around, say, the x-axis and ask, what's the volume of the resulting solid? Many, many questions of a calculus nature, and we will be investigating some of these after we spend a little bit more time talking about parametric equations and how to handle them in general. Until our next video, I wish you good health. Stay well. I'll see you then.